So welcome to lecture of Power System Dynamics course, Dynamics and Control course. So yesterday we were discussing about the modal matrices, right? So we'll continue in fact that how this modal matrices plays an important role in stability analysis, particularly the small signal stability analysis. Okay. So let us continue. So last class, what we have studied that we have choose a new state vector that is in fact corresponding to each of the eigenvalue, right? So, and by substituting, we found this is your uh, now this is your new state space model, right? Z dot Zi dot is equal to lambda I Zi t. So for I equal to 1 to n, that means corresponding to each of the eigenvalue, we have written equation in a decoupled manner, and that is how it will represent different modes of a system, because we wrote xt x equal to phi of zt, right? So here we can see this xt is not a decoupled equation in terms of the eigenvalues, but whereas when we write zt, when we substitute this xt equal to, because we know xt equal to ax plus bu, so this is not a xt dot is equal to ax plus bu. So this is not in fact decoupled equation, right? So now if we'll substitute xt equal to phi zt in this equation and just pre-multiplying phi inverse, we'll find a diagonal element here, diagonal matrix here, right? And that will make this equation decoupled. That means we'll get each of the new state variable corresponding to each of the eigenvalues in a decoupled manner. Therefore, this new state variables, they will be known as different modes of a particular state. So a particular state is having, it is a combination of different modes. You can see here from this equation, this particular state is combination of different modes. And each of the new state variable, that is zt, will be known as a mode of a particular state, right? So now the solution of the above equation with initial condition, if we'll take Zi naught, then obviously the solution of this differential equation Z dot t equal to lambda I zt will be Zi t will be equal to e to the power lambda I t Zi naught, right? Zi naught is your initial condition, and it is valid for I equal to 1 to n for each of the state variable. Right. So from this equation, the stability of the system can be easily assessed, right? Already we discussed this. If the eigenvalues are on the left half of the S-plane, then obviously it will be asymptotically stable. That means the stability is known as asymptotic stability, right? Okay. So, and also if one of the eigenvalue is in the right half of the S-plane, then this will be aperiodic instability, right? That means it is the system is unstable, right? So because one of the mode, when one of the eigenvalue is in the right half plane, so one of the mode becomes unstable. That means your system becomes unstable, right? And also the eigenvalues of a system with real state matrix have complex conjugate pairs, and if at least one of the complex conjugate pair lies on the imaginary axis of the S-plane, then the system becomes oscillatory, right? And this is known as oscillatory instability. Sometimes this oscillatory instability, when it is not properly damped, under that condition it will become unstable. The system becomes unstable. So And also finally, if one of the eigenvalue lies in the origin, then the system stability cannot be assessed. Already we have seen this. And we know this equation xt equal to phi zt. We have considered this. From this equation, the initial value of the original state vector in terms of the new state vector can be written as this. So the initial value, we can write this for the in terms of new state vector, and then just by taking inverse of phi, we'll get ZO is in terms of the initial value of the state vector, that is psi of XO. And we can write one particular element, ZIO will be equal to psi I XO, right? And now I can write ZIT, that is equal to e to the power lambda IT ZIO, right? Now this I can substitute in xt equation, right? If I want to find xt, the state vector, then I can substitute this, right? So easily I can write the equation, and along with the initial value of the state vectors or state variables, right? So that is how if I'll write xt equal to phi of zt. So zt I know, zt I can substitute this, okay? And ZIO also I can substitute psi of XO, right? Okay. So this is how I can get the state vectors. That means the time domain response of the state variables. So now since the new state variables ZT are directly related to eigenvalues, and each of the new state variables corresponds to exactly one eigenvalue, and therefore it is called mode, right? Mode matrix or different modes of the system. So it can be observed from the equation that the right eigenvector phi I corresponds to the activity of the state variable x in the ith mode, right? So we know that xt equal to phi of zt, right? So if I little bit expand this, if I'll write for one element only xjt, so how this equation will look like? This will look like sum of phi of ji zit, right? So I is 1 to n. So that means the ith state variable is a combination of different modes. So you can see here different modes, right? So like if I'll expand this, I can write this as phi of j1 z1t plus phi of j2 z2t plus dotted up to phi of jn znt, right? So we can see this state variable jth state variable is a combination of all the modes, right? If now I will find what will be the activity of the state variable jth state variable, that is xj, in the ith mode. That means ith mode I can write here as ith mode this phi of ji zit, right? So this is the ith mode, right? So this activity of the jth state variable in the ith mode will be decided by this right eigenvector phi, right eigenvalue, sorry, element of the right eigenvector phi ji, right? So this is one of the element of the uh, jth, we can say it here, ith eigenvector, right? So this is one of the element of the ith eigenvector phi I. So therefore here it is mentioned, you can see that the right eigenvector phi I corresponds to the activity of the state variables xt in ith mode. Okay. So this xt, that means your state vector, the activity of the state vector in the ith mode will be decided by this right eigenvector phi I, right? That means if what it means, in fact, it means that the state variable already I explained, the state variable xj. For example, the state variable xj activity in the ith mode is given by the magnitude of the element phi ji, right? Like I have explained here. So this element of the phi ji, the element phi ji of ith right eigenvector will give the activity of the jth magnitude, right? Jth state variable in the ith mode, right? So the magnitude will give the activity, and simultaneously it will the angle of this phi ji will give us the direction of its activity. Okay, so that is what it is mentioned here. Because it is a complex quantity, so it has one magnitude and angle. So magnitude will give us the magnitude of the activity of the state variable, jth state variable, whereas the angle will give us the direction of the activity of the jth state variable in the ith mode, right? So now, similarly, psi I shows the contribution of the state variable xt in the ith mode. How it is? We can see here the equation already we know that zt I can write it as psi of xt, right? Okay. So therefore, if we'll expand this, how it will be, how it will look like? It will look like Z1t, Z2t dotted up to ZIT dotted up to ZNT. So this will be equal to psi of 1 dotted up to psi of n. Here it will be x1, x2 dotted up to xn, right? So now if I'll multiply it, it will give me psi 1 x1 plus psi 2 x2 rated up to psi n xn, right? So the size of this will be psi 1, we know psi 1 is sorry, this matrix is a n by n matrix. So sorry, it will be a column matrix. In fact, it will be psi 1 transpose, then psi 2 transpose, rated up to psi n transpose of transpose, right? So this is psi matrix. So now if I'll expand this, it will look like this. So now it will become psi of, if I'll suppose write one element in the Z matrix, that is, let us say ZIT. So ZIT will be nothing but psi psi I. So the ZIT will be your psi 1. If you'll write psi 1 is psi 1 1 1 1 2 dotted up to psi 1n, right? This is a row vector, and similarly your psi 2, and if we'll come to psi I, so psi 2 also like that, psi 2 1 psi 2 2 dotted up to psi 2n, right? Okay, so now if I'll write this z it will become this psi 2. So zit, it will become psi of this is of size n by n. This is n by 1, right? So if we'll multiply this, it will give us summation of psi of ij x, sorry, x of xj, okay, xj j equal to 1 to n, right? So that will give me psi of 1 x1 plus psi of 1 to x2 related up to psi of 1 I x, sorry, I, here it will be I, I1, I2, and it will be I j xj related up to psi of in xn, right? So that means what it indicates that this psi I will in fact show the contribution of the state variable xt in the ith mode, right? So we can see here, this is your mode element of the mode vector, right? Mode matrix, you can say. So ZIT, where we can see the contribution of xt means it is all x1, x2, or dotted up to xn, all the state variables. So contribution of all the state variables in the ith mode is described by this ith left eigenvector, right? So psi I, in fact, we know psi I is psi I1, psi I2 dotted up to psi In. So this is the ith left eigenvector, and which indicates in fact the contribution of the state variables xt in the ith mode, right? We can see here from this equation. So each of the element of this left eigenvector will give us the contribution of each of the state variables, right? Okay, so this is how it gives us. That means your left eigenvector indicates the contribution of the state variables in the ith mode, in a particular mode. Okay, and the right eigenvector indicates the activity of the state variable in a particular mode, right? So this is the difference between right eigenvector and the left eigenvector. So now I can see it from this. For example, psi ij shows the contribution of the state variable xj in the ith mode, right? Already I have shown this. This is your contribution of the state variable xj in the ith mode. Psi ij indicates this, right? Okay, so now the total effect. So in order to find the total effect of the state variable in the ith mode, we need to define a variable that is known as the participation matrix. So the total effect of the activity and the contribution of a state variable xj in the ith mode can be given by phi ji into psi ij. So phi ij gives us the activity of the jth state variable in the ith mode, and psi ij indicates the contribution of the jth state variable in the ith mode, right? So therefore both phi ji and psi ij, they are important. So by combining these two, this will give us the participation of the jth state variable in the ith mode. Okay, so this phi ij into psi ij combinedly is known as participation of jth state variable in the ith mode. Okay, participation of jth state variable in ith mode. Okay. Now, the combined effect of the activity and contribution of a state variable in a particular mode can be represented as a matrix form, and that matrix is known as, because this is one of the participation of the jth state variable. So by taking all these elements together, we call it participation matrix, right? And that can be represented by a matrix that is called participation factor matrix. So the participation factor matrix can be given as this. We can see here, P is the participation factor matrix here, which has vector elements P1, P2, Pn, right? So it is a n by n matrix, and one of the vector p1, p2, pn. Suppose pi I want to mention, so pi will be nothing but the elements of pi will be phi of 1i, psi I1, phi of 2i, psi I2, that up to phi of ni, psi of in. So this is the one of the vector ith participation vector in the participation matrix. Okay, and this includes this also, this is valid for I equal to 1 to n modes. Okay, so as the right and left eigenvectors are normalized, the sum of the elements, we know that right and left eigenvectors are normalized, and we know this, that this is valid, that psi phi is equal to I, right? This is the identity matrix, or uh, we say that phi of psi of ij into phi of ji is equal to 1, right? So therefore, as this is normalized, therefore uh, the participation factor matrix corresponding to a particular mode, that is ith mode, that will become equal to 1. That means the sum of the elements of the participation matrix corresponding to ith mode will be 1, right? So if we'll write the participation matrix like this, let me write it. It is equal to p1, p2, pn, right? And let us say pi is here somewhere in between. So if I'll expand this, it will look like um, phi of 1 1, phi of 1 1, psi 1 1, phi of 2 1, psi 1 2, dated up to phi of 2i, sorry, phi of 2, phi of n1, psi of 1n, right? This is the first element, first vector. Then second vector will be phi of 1 2, psi of 2 1, phi of 2 2, psi of 2 2, right? So this will give me phi of n2, psi of n2, psi of 2n, right? And similarly, if I'll write ith element, I can write it as psi of 1i, phi of I1, phi of 2i, psi of I2, rated up to phi of ni, psi of in. Right. Then the nth element I can write, nth element, the nth vector will be, nth participation vector will be phi of 1n, psi of n1, phi of 2n, psi of n2, dotted up to phi of nn, psi of nn, right? So this is your participation matrix. Now, if we'll put the state variables and the modes, so the modes will corresponding to each of the columns, right? So this column will correspond to the ith mode, right? If I'll take sum of these elements corresponding to a particular mode, let us say ith mode, then that will become equal to 1. If we'll sum it up, it will become 1. And if we'll sum, similarly the sum of the elements of the participation factor matrix corresponding to kth state vector, so corresponding to a particular state vector, so if we'll add row wise, that will also give me 1, right? This you can test it because it is very easy to find. So I'll also give another assignment regarding this. You can test it. So how it will become 1? It's corresponding to ith mode and corresponding to kth state, any of the state. That means if we'll add the elements column wise of a particular column in the participation matrix, that will give me, the summation will give me 1. And also if we'll add row wise of a particular row, the sum of the elements in a particular row, that will also give me 1, right? So you can easily understand how it will become 1 because all these elements are in fact normalized, right? So now we can um, go further. You can do this analysis, or else I'll give one of the assignment. As one of the assignment, you can do it in your home, right? Okay. So now we'll talk about controllability and observability. Okay. So how this plays an important role and how it affects different modes, this controllability and observability. So we know this is your state space model of the system. If I'll represent the power system also, I can represent this after linearization, right? So we'll talk about how to linearize a nonlinear system like power system, right? So this state space model, we have x dot t is equal to axt plus but. This is a general state space model, and output equation is y equal to cxt plus dut. So now substituting xt equal to z phi t, that is in the new state variable, or we call it mode matrix, right? So just by substituting this, we'll find phi z dot t will be equal to this. Now just multiplying phi inverse in the first equation, so we'll find z dot t will be equal to the diagonal matrix into zt plus phi inverse but, and your output vector will be yt will be equal to c phi t zt plus dut, right? So now if we'll see this equation, this phi inverse b and c phi, they plays very important role in observability of the system and controllability of the system corresponding to each of the modes, right? So this is the new state space model corresponding to each of the modes, right? Z dot t equal to diagonal matrix zt plus phi inverse v ut, right? And ut is your control input. So now I can write just phi dash b. I can write phi inverse b. I can write b dash and your c phi I can represent c dash. Okay, so b dash is nothing but is equal to phi inverse b. So now I can write this equation, and then referring to the above equation, now if we'll see, now if we'll consider ith row of the matrix b dash, and if by chance if the row of matrix b dash becomes 0, so this b dash matrix row, all the rows becomes 0, then the input has no effect on the ith mode, because this gives us mode, right? Different modes. So control input has no effect on ith mode. That means your ith mode is uncontrollable when the row matrix of b dash becomes 0. If it is not 0, if any of the element is non-zero, then it is controllable, right? So that means the ith mode becomes uncontrollable when the ith row of the b dash matrix becomes 0, right? Similarly, if we can observe that ith column of the c dash matrix, right, which determines whether zi contributes to the formation of output, right? That means this is your mode matrix where this will say that whether it is contributing to the output or not. That means whether it is observable in the output or not. This will be decided by this C dash matrix, right? Sorry, this will be not, there will be no phi here, only C dash ZT. Okay, so phi will be removed. So this will C dash ZD. So the C dash matrix will decide the observability of the different modes, right? So if ith column of the C dash matrix is 0, then what will happen? Your ith mode is not observable in the output, right? So that means your ith mode is unobservable. Okay. So similarly, if any element of the C dash matrix is 0, that means one of the mode is unobservable in the output, right? Similarly, we can say uncontrollability also, right? So therefore, B dash is known as controllability matrix and C dash is known as mode observability matrix. Okay, so B dash in fact decides whether a particular mode is controllable or not, right? So by through this B dash matrix, and C dash matrix decides the observability of the different modes in the output, right? So by inspecting B dash and C dash, we can classify modes into controllable and observable, controllable and unobservable, uncontrollable and observable, and uncontrollable and unobservable. Therefore, we can divide into four categories of the modes. So based on the C dash and B dash matrix, B dash and C dash matrix, we can decide what type of modes existing in the system, right? So now we'll talk about how we can linearize a nonlinear system. A general concept we'll discuss. What is the process of linearizing a nonlinear system? Because power system is a nonlinear system. So if we write the equation of the system, already we have seen the dynamic equations related to the power system, and we have modeled all the components, and it is found that it is a nonlinear uh, differential equation, right? So that means nonlinear differential algebraic equation. So in order to analyze the small signal stability, we need to linearize this nonlinear system, and so that we can find the state space model very easily, right? So the model or eigenvalue analysis can be done for a dynamic system which is linear. It cannot be possible for a nonlinear system. Therefore, a nonlinear system cannot be expressed in the state space form, and hence eigenvalue analysis cannot be used for a dynamic system which is nonlinear, right? So one way of overcoming this problem is to linearize the nonlinear system around a small region of its steady state operating point. So if we can linearize this nonlinear system around the steady state operating point, then this problem will be overcome. So let a nonlinear dynamic system be represented as this: x dot equal to f of xu, right? And let the steady state condition values of xu, that is x is the state vector and u is the input variable or control input. If we can find the initial values as xo and yuo, so then if the system dynamic variables and inputs are perturbed by a small value, that is delta x and delta u, from the steady state operating point, then from this equation we can just substitute, if we'll substitute the perturbed value, that is x equal to xo plus delta x and u equal to uo plus delta u. Just by substituting these two in this equation, we'll get x dot xo dot plus delta x dot equal to f of xo plus delta x uo plus delta u, right? So if we can expand this, this is a function of x and u. So if we'll expand this using the Taylor series expansion, so the right hand side can be expanded using Taylor series expansion, and if we'll neglect the second and higher order terms, then what equation we'll find in the right hand side? The right hand side will look like f of xo uo plus delta f by delta x, that is evaluated at x equal to xo, u equal to uo, into delta x plus delta f by delta u evaluated at x equal to xo, u equal to uo, into delta u, right? Now we know xo dot is equal to f of xo uo, right? So now this will be cancelled from both the side, and if we'll find delta x dot, so delta x dot will be equal to delta f by delta x. So evaluated at x equal to xo and u equal to uo into delta x, and delta f upon delta u, that is evaluated at x equal to xo, u equal to uo into delta u. So now this is a matrix, right? And this is in the they are all constants because evaluated at initial values, right? So therefore, let us assume A equal to this delta f by delta x evaluated at xo and uo, and B equal to delta f by delta u evaluated at xo and uo. So then we can write the equation delta x dot equal to A delta x plus B delta u, right? So A and B we can find from the initial conditions by taking the derivative, partial derivative with respect to the state variables and the input variables, right? So the system given by the above equation is now a linear system. This is now a linear system, right? And the stability of which is decided by the eigenvalues of the state matrix. So this will give us the stability of the system, right? And also we can do the modal analysis on this. So this process of converting a nonlinear system to a linear system for a small disturbance around the steady state operating point as given above is called the linearization process. So this is the linearization process. Already you know this maybe in your previous courses. So this is for your remembrance only. Similarly, the output equation can be written in the linearized form as this. So similarly, we can also linearize the output equation, and that will look like delta y equal to c of delta x plus d of delta u. And c will be obviously what? C will be delta of, if it is a function of g, then delta g by delta x. Okay, delta g by delta x at x equal to xo, u equal to uo, and d is equal to delta g upon delta u, x equal to xo and u equal to uo, right? So this is how we can find the output equation also in linearized form, right? So now let us consider one example, small example, and let us find let us do the modal analysis on this. So this is a small circuit given RLC circuit, that is having resistance, inductance and capacitance, and the output voltage is measured across the capacitance C, that is VO, and input voltage is VI, right? So now we need to study the eigen properties of the state matrix, and we need to carry out the modal analysis. So I hope you can all do this, but I'm showing you here. You can just see it, and this is a very small example we are considering. So if you write the equation just by applying KVL and KCL, it will look like LC d square VO by dt square plus RC dVO. VO is your output voltage by dt plus VO equal to VI, right? So now just dividing LC both the side, we'll find this equation, right? So 1 by LC will be divided and it will become d square VO by dt square plus 1 twice of zeta omega n. We know omega n is 1 by LC root 2 and zeta is L by C. Okay, so omega n square VO, right? So this will be the equation, and omega n is 1 by LC square root and zeta is R by 2 L by C square root, damping ratio, right? And omega n is undamped natural frequency. So now if we'll define the state variables, now your xo, let us consider x1 is equal to VO and x2 equal to dVO by dt, and u equal to Vi and y equal to Vo, that is output voltage across the capacitance, right? So now y is equal to x1. This is your output equation now, right? Y equal to x1. Now if we'll substitute these state variables in the differential equation, we'll find dx1 by dt will be equal to x2, right? So that is x2 is dVO by dt, right? and dx2 by dt, that is nothing but equal to d squared vo by dt square, that will be equal to minus omega n square x1. So x1 is here vo, right, this one, minus 2 zeta omega n x2, here this one, plus omega n square u. So now this is your state space model, right? Because here there is no nonlinearity involved here, because this is a linear system, right? RLC circuit is a linear system, so therefore there is no nonlinearity involved in this. So therefore we know there is no need of linearizing these equations. Already it is a linear differential equation, right? So therefore now we can write the state space model. So x1 dot x2 dot will be equal to 0 1 omega n minus omega n square minus 2 zeta omega n, x1 x2 plus 0 omega n square u, right? So this is how these two equations I can write, represent in the state space form, right? And also y will be equal to 1 0 x1 x2 plus 0 u, right? So this is your state vector, and this is the differentiation of state vector, and this is your output equation, right? So both equations are there. So now we can see the A matrix. This is your A matrix. This is your B matrix, right? And this is your C matrix. This is your D matrix. D matrix is 0, right? So now from the A matrix, we can see here, from the A matrix, we can find the eigenvalues just by using the equation how to find the eigenvalue. We know already, right? Lambda A minus lambda I, we substitute generally, A minus lambda I, determinant of this equal to 0. So determinant of A minus lambda I equal to 0. So that will give me minus lambda 1 minus omega n square minus 2 zeta omega n minus lambda. So if we'll find the determinant and equate to 0, it will give us this equation, that is lambda square plus 2 zeta omega n lambda plus omega n square equal to 0. So now this is a very well-known equation, and from this equation, this is also known as characteristic equation, and from this equation we can find the values of lambda, or the roots of the characteristic equation will give us the values of the eigenvalues. So here we will get two eigenvalues. So one is lambda 1, that is equal to minus zeta omega n plus omega n square root of zeta square minus 1, and lambda 2 will be equal to minus zeta omega n minus omega n zeta square minus 1 square root. Okay. So with both these eigenvalues, we can now form from the model matrices, like we can find the right eigenvector matrix and the left eigenvector matrix. Then we'll find the modal analysis. Then we'll do the modal analysis on this, right? So let us do this. So we know A minus lambda I into phi equal to 0, right? So this is the equation from where we'll find the right eigenvector matrix phi. So now just substituting this right eigenvector for ith variable, for ith eigenvalue, we can say it is phi 1i, phi 2i, right? And this matrix will become minus lambda I 1 minus omega n square 2 zeta omega n minus lambda I, that will be equal to 0. And from this equation we'll get two separate equations, and they're in fact not independent equations. Okay, so now therefore we need to assume a particular value for phi 1i or phi 2i. If we'll assume one value, we can find the second value, right? So let us fix phi 1i as 1, and then we can determine phi 2i. So if we'll fix phi 1i equal to 1, we can find this phi 1. That means your eigenvector for corresponding to the first eigenvalue will become phi 1 1, we assumed 1, right? So therefore your phi 2 1 will become lambda 1. So it will become, so just substituting the value of lambda 1, we'll find phi 1. Similarly, we'll find phi 2 by substituting the value by assuming phi 1 2 as 1. By assuming this value for phi 1 2, we can find phi 2 2 as lambda 2, right? Okay. So now if we'll do the model analysis from here, we can find, okay, so before that we can find the left eigenvector matrices. So your left eigenvector matrices, if we'll calculate, it will be found to be this. So your left eigenvector will become this. So psi is 1 1 minus lambda 1 by omega n square minus lambda 2 by omega n square, right? And we know right eigenvector is this, and we found left eigenvector matrix. Both we found, right? So now therefore we need to normalize this, because we know psi and phi will become Ci, right? Or we can say a Ci. That means C is a matrix, it is having the constant values, right? So now if we'll do this, we can see just multiply phi, psi and phi. After multiplying these two matrices, we'll find this will be 0, right? Because lambda 1, lambda 2 is lambda 1, lambda 2 is nothing but equal to omega n square. So therefore it will become 1, and this term will become 0, this term will become 0. So only this and this term will be there. So that means it is equal to C of I, right? C into identity matrix, and C is having two elements C1 and C2. C1 is this, right? This is your C1, this is your C2, right? Okay. So now how to normalize and how to get the normalized eigenvectors, left and right eigenvectors. If we'll keep the right eigenvector as it is, and we want to normalize this psi just by dividing C1 in the first element and C2 in the first element, in the second element, right, of the, sorry, second vector of the psi1 of the psi matrix, of the left eigenvector matrix, then we'll get uh, the normalized psi and phi, right? So already we know how to normalize. We can see if we have two variables x1 and x2 that is giving a constant value, right? So how to normalize it? So if we'll divide both sides c, the constant, x1 x2 by c, that is equal to 1. That means your normalized value, if I want to find, if I want to keep the x2 as it is with the previous value, then your x1 will be modified by 1 by c, right? If I want to keep x1 as it is, then your x2 will be modified by 1 by c. So here I want to keep x2 as it is, so therefore x1 will be divided by c, and this will be the normalized value for x1 and x2. And if we'll multiply both, that will give me 1, right? So similarly here in this case also we'll do the same thing. In order to normalize psi and phi, we need to divide these C1 and C2 in the psi1 column vector, psi1 row vector and psi2 row vector. Then we'll find the normalized value of psi and phi both, because I want to keep the values of phi as it is. We want to keep it fixed. I want to change this psi value in order to normalize the equation. So therefore your now your equation, your psi and phi will become like this. If you'll see your psi will look like this, because I divided this 1 minus lambda 1 square by omega n square in the row of in psi1 vector and psi2 vector. This is your psi1 vector, this is your psi2 vector. So if I'll divide, I'll find this, sorry, this one. Now your psi will become omega n square by omega n square minus lambda 1 square minus lambda 1 square by minus lambda 1 by omega n square minus lambda 1 square. And this will be your C1, sorry, psi1. This is your psi1. This is your psi2, right? Okay, this is your psi2. And this is your phi1. This is your phi2. Okay. So now we can do the modal analysis. Just for the purpose of checking, if I'll see here, if I can multiply here psi1 into phi1, right? So that will give me 1, in fact, right? So it is just for checking purpose. And when I will multiply here psi2 into, sorry, psi1 into phi2 here, if I'll multiply, it will give me 0, right? So that is, this is for the checking purpose, and it is found that psi and phi matrices are correct. And now I want to find the participation matrix. So through the participation matrix only I can know the contribution and activity and contribution of state vectors or state variables in each of the modes, right? So now in order to find the participation matrix, here we have two vectors in the participation matrix. One is P1 and P2 corresponding to each of the mode, right? So corresponding to each of the eigenvalue or each of the modes. So P1 and P2, right? So, so the element of P1 is P11, P21, and element of P2 is P12 and P22, right? Okay, so P2 is P12 and P22, right? Okay, so now if I'll find P11, so this will be phi11, psi11, P21 is psi21, psi12, right? So all the elements of P matrix I can find, and then after multiplying these variables or these eigenvector elements, right? So I will find each of the elements, right? Now I can check for each of the mode and each of the state variable whether the sum of the column and the sum of the rows, sum of the elements in a particular row, sum of the element in a particular column is becoming 1 or not. Just for the checking purpose, you can do this. So if I'll add this sum of the columns P11, P21, that will give me P11 plus P21, that will give me psi11, sorry, phi11 into psi11 plus 21 is phi21 psi12. So if we'll multiply these elements and add this, it will give me 1. Just check it. It is obviously you will find the value 1, right? And similarly, if I'll add a particular row, that is, let us say first row, so P11 plus P12, that is P11 is phi11 psi11 plus P12 is phi12 psi21. If we'll add this, this will also lead to 1, right? Just check it and let me know if you are not getting, right? So obviously you will get it 1, right? So this is for the checking purpose, you can do it. Now the participation matrix, after finding, you can know the activity and the contribution of the each state in each of the modes, right? Okay, so then we'll do the small signal stability analysis of a single mesh and infinite bus system. So we are considering here is a single mesh and infinite bus system which is connected to a large system, and there are two parallel transmission lines, and certainly there are some charging impedances. So we'll discuss this in the next class because this will take time to uh, to accomplish it. So therefore, we'll discuss it in the next class tomorrow. Okay. So thank you very much.